All right. So, for homework today, we had our merge sort assignment. I gave you a starting point. This should have been difficult for most of you. Recursion is almost always a tough thing to wrap your mind around. The best way to learn recursion and learn about merge sort, unfortunately, is to throw students into the deep end, have you grapple with it for a while until you give up. And then when you see how it works, it makes more sense than if you just see somebody solve it the first time. So it is what it is. Um, what's interesting is when some of you who are software engineering majors, you'll eventually have the language theory class um, where we use a programming language in there called Scheme, which is a superset of an older language called Lisp. And that language doesn't have loops. So you actually have to implement everything recursively. So when you come out of that class, you actually have a really strong understanding of recursion and you find it difficult to think iteratively again. So recursion is not as hard as it maybe initially sounds, but it is a difficult topic to wrap your mind around initially. All right. So let's go through and understand what the code's doing currently. It's wasn't doing a ton. So I created this class called sorter, and sorter maintains an array of integers. When you build an instance of sorter, you tell it how many things you want to have in that array. So you see out here in driver, I said I want to build a sorter that is going to have 10 things in there. You can change that number to whatever you want. Um, Then I went through and I just filled that up with random numbers between 0 and 99. So it's filled up with a bunch of random numbers. All right. Then I have a function inside of sorter that's going to be a non-static function since I'm calling it with an instance of the class. So s dot display current state of the array. This is going to go through and it's going to spit out the array all on one line and then press enter, kick it down to the next line. That way it's easier to visualize instead of having a whole bunch of numbers right on top of each other. Then I'm making a call to merge sort here, which currently does nothing. Well, merge sort does do something right now. What it does is it calls a second version of merge sort that takes in a beginning and end. That is the portion of the list that that particular call to merge sort is messing with. The initial call is the entire array, right? From beginning to end. The next call well, the next two calls will be the first half, beginning to end, the second half, beginning to end. Rinse, lather, repeat. All right. So right now I make that initial call to merge sort saying the beginning is 0, the end is the length minus 1, which is the last legal bucket in the entire array. Okay. Homework was to basically fill out those two things such that out here you'll get your numbers randomized. And then after you call merge sort, if it was working, they will now be in order. Initially, they're both randomized of the same list of random stuff. All right, so now we have to get to work. So what we're going to do is we're going to approach this in a couple of steps. What we want to do is we want to see we want to see that we are calling merge sort on the correct portions of the list. So each time we call merge sort, instead of doing any sort of sorting currently, we're just going to display the portion of the list that that guy was interested in. All right, to make sure that it's kind of doing that divide and conquer type thing. So you know you're working with the right stuff. So what I'm going to do here in sorter is I'm going to create a second version of display current state of the array. I'll make this guy private since I don't anticipate calling this outside of here. Um, let's call it display current state of array. And this guy will take in an int begin, and an int end. All right. So his job is going to be to loop through that array and display only the things in that little sequence. So I'm going to steal this for loop here. And I'm going to go from begin all the way up to less than or equal to end and display whatever thing I found there. So if I pass in 0 for begin and 3 for end, it'll show bucket 0, bucket 1, bucket 2, and bucket 3. All right, so a subset of the entire array. All right, so now we have a second version of this guy. Inside of merge sort, what I'm going to do initially is I'm going to go ahead and I'm going to ask the question, is this sorted? If you remember in class last time, and you probably also saw it in the video, a trivially sorted list is a list where begin and end are the same number. Okay, so if begin is not equal to end, that means this is not a sorted list. So if begin is not equal to end, we'll go ahead and display the current state of our list. Actually, we can do that regardless. All right, so if begin, so we'll display from begin to end. Then if begin is not equal to end, that means we are not quite sorted yet. And if we're not quite sorted yet, that means we need to now call merge sort on the left half of the part we're working with and the right half, the part we're working with. So that's where this next step comes in. So we're going to have to keep track of maybe 4 variables: a begin 1, a begin 2, an end 1, and an end 2. So we'll say int begin 1. That guy will be the actual begin of whatever was passed in. That's going to be the far left of the left half. Int end 2 is going to be equal to whatever end was passed in. Those are the easy ones, right? Beginning of the whole thing, the ending of the whole thing. Go ahead. Open parentheses. What are we talking about?
Never mind.
Okay. Yeah, maybe it was while I was in the process of writing it. Right. I just wrote this. You have this guy. You have the one that just shows the entire thing. I just wrote an internal private one that allows me just to display the current portion of the array that we're currently looking at, to kind of prove to ourselves that at the very least we have the microscope on the right part of the array, that this particular call to merge sort is in charge of sorting. All right, so we'll go ahead and regardless of, I can even say this dot, regardless of whether or not this is a one list or not, we'll go ahead and just display the entirety of that list. Then we're going to ask the question, if this guy is not currently sorted, well, then I'm going to want to call merge sort in the left half, and then I'm going to call merge sort in the right half. Why? Because that's how you sort lists. You call merge sort on them. This is that recursive call piece. So the beginning of the left half will be whatever begin was. The ending of the right half will be whatever end is. Int end 1, a little question mark there for a second. And then int begin 2 is going to be equal to end 1 plus 1. Okay, so we have all of them filled in right now, except for the magic. The one thing that probably was the difficult thing to figure out. A lot of times the path that people go down is something like, oh, well, maybe we do n minus begin divided by 2, something like that, which works for the left half stuff. But then in the right half, you start getting crossover. And so the way to figure out this is begin plus end divided by 2. So initially, let's go to our slides here. If this was our array, this guy right here, and begin was bucket 0, and n was 0, 1, 2, 3, 4. 4 plus 0 divided by 2 is 2. So that would be the end of the first half. Now, what if you were only dealing with these first three? So that's 0 and 2. 2 plus 0 is 2 divided by 2 is 1. So there's the end of the first half. Where the check comes in is the second part. What if the second half of your array was 0, 1, 2, 3, and 4? 4 plus 3 is 7, divided by 2 is 3. So that's where you get your beginning and end of that second half. All right, so the math for doing that is begin plus n divided by 2. And then your second begin is 1 greater than that. If that's the end of the first half, then the beginning of the second half is 1 element after that. Make sense? All right. So those are our 4 things there. And since we know we're not dealing with a 1 list, means it's not sorted, we then have the responsibility to sort the left half and sort the right half. And how do we do that? We call merge sort on begin 1, end 1. We call merge sort on begin 2, end 2. That's what we do. If it's not a 1 list, figure out where the beginning and ending of the first half and second half is, call merge sort twice. Once for the first half, once for the second half. Go ahead. We're not disregarding all the elements in between. There will be a different recursive call that deals with those. If you go back and look at this guy, we kept dividing the list up. So this call to merge sort dealt with buckets 0 to 2. This call to merge sort dealt with buckets 3 and 4. This call to merge sort dealt with 0 to 1. This call to merge sort dealt with just bucket 2. And then there would have been a bunch of calls here on the right half as well. So we are dealing with all the different values. We are just dealing with them in chunks at a time, half of the half of the half of the half. And because we're passing things around as pointers, when we update a little section of our array, that update is permanent to the rest of the array, so everybody else notices it. Now, what we want to make sure we're doing, though, is that we don't get crossover with merge sort, where you don't have 2 different calls to merge sort making changes to the same place in your array. Okay, so that's why kind of doing this initial step of, let's make sure I'm dividing my arrays up correctly before I go and start sorting stuff. All right, so that's what we hope to have here, is that we would see the whole array. We would see then the first half. We would then see the half of that, the half of that, the second half of that, so on and so forth. All right, so this call to merge sort is a recursive call. It is calling the same function here, just passing it a different beginning and ending that it wants that call should focus on. And this does block, meaning that we won't even get to the second call to merge sort until this call has completely finished. And keep in mind, when we make that call, inside that call, we might be making 2 more calls. And inside of that call, each of those calls, we will be making 2 more calls until we finally get to a situation where begin is equal to end. When begin and end are the same, that means we are only looking at a single element. And by definition, a single element is already in order. It's sorted. All right. So display everything we're supposed to display on a particular list. So if we go back in here, we run this guy. Let's look at what we got here. Forget about, this is my second, actually that's the first call to merge sort that shows the whole thing. Then notice we're looking at just the left half of that list. Then we're looking at just the left half of that list. Then we're looking at just the left half of that list. Then we're looking at the left half of that list, which is the 1 list, so it's already sorted. which then allows us to jump back up and look at the right half of that list, which is a one list they're already done, which then lets us jump back up and look at the right half of that list, which is a one list, so we're done, which then lets us jump back up and look at the right half of that list, 40 and 60, which then is going to show us a 40 and then a 60. The left half, it's a one list, bounce back up. Right half, it's a one list, bounce back up. We're not doing any merging stuff. So at this point, we're not actually doing any sorting. We're just kind of hitting the highlight reel, pointing out the places that we intend to sort. All right. I guess technically we are doing everything we can to sort a list of one, which is basically just saying I'm done and moving on. All right. Next thing we look at, we're seeing 24, 9, 1, 39, and 4. And that's the right half of the original list. So after all those calls, we finally got back to the original second call. After all those jump going down the line, we finally get back to that right half of our original call. And then we get the left half of that guy, the left half of that one, the left half of that one, bounce back up because it's a one list, the right half of that one, bounce back up, it's a one list, then the right half of this one, which will be a one, bounce back up. Then we get the right half of this guy, which will be 39 and 4. Left half of that, 39, one list. Right half of that, 4, one list. And then we're back to our top where had we actually done some sorting in here, those guys should now be in order. All right. So what we've done here is we've just taken that voyage through all the recursive calls, showing ourselves that we are looking at all the correct places in the correct sections of the list, as as it were, but we haven't done the sorting yet. So now we at least know we're hitting the highlights. Go ahead. It repeats itself because I'm calling merge sort multiple times. Effectively, you can think of this as building in a loop. It creates this circle. Now, one thing I will mention about recursion, though, and this is something, I kind of mentioned recursion is difficult. It's because it's hard to wrap our mind around that. Okay. I want to sort this entire list. So I'm going to call merge sort. Well, it's, now I'm going to sort the left half. And I'm going to sort the right half. Do I have a tool laying around that knows how to sort stuff? Yeah, merge sort. Call merge sort on the left, call merge sort on the right. Well, now this guy's still not sorted. I need to sort the left and the right. Do I have a tool laying around that knows how to sort that? Yep, call merge sort. So we'll keep calling merge sort. So typically, if you can talk your way through it, you'll implement the recursion yourself. If you don't treat this merge sort tool, in this case, that's our recursive thing we're calling, if you don't treat this as some sort of specialty thing, it's a tool that you give a portion of an array to and it sorts that portion. That's its job. All right. So we're just going to keep using this tool over and over again. So recursion, this is when a function calls itself from within itself. First thing to keep in mind here. So it was good that she brought up was how is it repeating all this stuff without a while loop? Effectively, something very similar to what's happening in a while loop is occurring, right? We are doing something multiple times, just our mechanism for that, instead of looping back up in a for loop, for example, or a while loop and adding something to it, our iteration occurs through recursive calls. Now, what's important about this is, first of all, recursion is not better than iteration. It's the right tool for the job. When do you use one versus another? Anything that can be done recursively can also be done iteratively with a loop and something called a stack. We learn about stacks in the next course, CSC 300 or whatever it is called these days. It used to be 300. All right, so that's our data structures course. So a stack, like a stack of magazines, we add things to the top of it, we remove things from the top of it. Push onto the top, pop from the top. That's a stack. Recursion effectively uses this behind the scenes, but kind of similar to how we've talked about the operating systems with our threads, how our threads only get so much CPU time at any point in time, things like that. And then I mentioned something probably in passing when we first started talking about that, something called a context switch, where the idea is when a thread or a process leaves the CPU, it has to pack all its bags up, but it needs to remember all the stuff so that next time it gets CPU time, it can kind of unpack its bags into the correct places to pick up where it left off, right? It doesn't start from scratch. We want every single time it gets CPU time to get a little bit more progress on where it was going. So context switching is expensive because we have to remember where we left off and remember the current state of all the variables, that kind of stuff. Recursion is the same thing. Okay. If we're back in this code right here, as soon as I make this first call to merge sort, I just paused the current call to merge sort. And this guy doesn't get to come back to his state until both of these dudes have finished. Okay. And we saw that inside of each of those, there's some more things that happen before it finally starts unwinding. So that means behind the scenes, however this language implements recursion, all of the current information about this call to merge sort, what its version of begin was, what its version of end was, what its version of each of these variables are, all that stuff has to be put on hold and stored so that when we come back to this, we can pick up where we left off. Okay. That's expensive, memory intensive. So recursion, we would often say recursive solutions are often short and elegant, but very memory inefficient. That doesn't mean don't do it. It means use it when it's the right tool for the job. All right. Um, so you might be able to solve a problem iteratively. You might be able to solve a problem recursively. If you can do it iteratively without a stack, because if you're using a stack, it's just as inefficient as this guy, because that's how recursion is typically implemented. You probably are going to benefit yourself speed and memory um, from those two perspectives. Yet sometimes recursion is the solution that makes the most sense, which is kind of interesting because it's also more difficult to think recursively because we have to think of that tool, that merge sort tool, as something that can be, if you have an axe, you can use that axe to chop a piece of wood in half. Then you can use that same axe to chop one of those halves of pieces of wood in half again. It's the same tool. You just targeted a different part of the same piece of wood. All right, so that's kind of what we're doing here. So recursion is probably not going to be your friend for a while, and it's actually something that you will not run into that often. But maybe 10% of the time, you might have a project that you're working on that would benefit from a recursive call. And once you have it in your toolbox, you'll be able to do that. All right. So if begin and end are not the same, figure out where the left half and the right half are. Call merge sort on the right half, call merge or left half, call merge sort on the right half. Once this guy returns, once we're right here, we assume that all of the elements in the right half, well, left half are sorted. We assume that all the elements in the right half are sorted. Why? Because they've already gone through the step that we're about to write, the merge step. All right. So the merge step, I think I put a function here for you to call, takes in a, why apparently I struggle with that word, begin. So it takes in a begin and end, and it's going to perform that merge step for that guy. So what am I going to do here? I'm going to call merge sort on begin and on end. Now, because we already had these values here, you could have had this guy, I'm sorry, merge, just merge, not merge sort. Because you already had these variables up here, you could have just passed all four in here, but we'll just recalculate them real quick. So merge, its job is to go through the first half of the list and the second half of the list and merge them together. So if we just look at that here quickly, I'm going to steal this. I'm going to put it out of order a little bit, and then we'll do the merge step. So let's do a 2 and a 1 and a 5, 3. I'm sorry, 3, 5, 7. This really needs to be like that. All right, I need to move some stuff around. So we're going to put the 2 here. We're going to put the 3 there. Not good enough. All right, so now it's good enough since the left half of our implementation is the larger half. So when we call merge step, we're looking at 2 separate halves of our list that have already gone through some battles, right? Things have already happened to these. Now notice that the left half is sorted in and of itself. The right half is sorted in and of itself. But the entire thing isn't necessarily in the correct order. Now remember, this is just a portion of the larger array that we're looking at. We're not looking at a copy of it. We're just looking at a snapshot of a single little space in the original array. So any changes we make here will be felt in other places in our program. Okay, because this guy was passed by reference. It's passed by reference because we're not passing it at all. Instead, our sorter class is just keeping track of that dude. So we have one array up here that everything is happening within. And when all is said and done, and we display that same array that we just displayed before this all started, it just happens to be in order now because it's gone through all these calls to merge sort. Okay. So I'm going to just steal those variables real quick. So when merge comes in, this is the begin and end of the thing we're the whole part of the array we're merging. I'm going to go ahead and get the left half and the right half. And then I'm going to create a couple of variables to keep track of where I am in the left half versus the right half. So we're going to say int start 1 is equal to begin 1. Int start 2 is equal to begin 2. All right, so start 1 and start 2 are that they're pointing to the beginning of our 2 parts of our list. So if you want to see this as a picture, this is start 1. That is start 2. Start 1 starts off pointing to the same place begin 1 points to. Start 2 starts off pointing to the same place begin 2 points to. Okay, so these guys are pointing to the beginning or of their respective lists. All right. Then what we do is we have to create a kind of a landing zone for our temporary sorting, a place that in this case is going to have 5 total buckets. So we want to create something like this. It's currently empty. And maybe we keep track of where we are in that guy with something called curpause or that. All right, so curpause will be 0, then 1, then 2, then 3, then 4, because as we're going through, we're merging this partially sorted list with this partially sorted list. We're going to be filling in this guy, and then at the end, we'll be overwriting these values with our new values in order. All right, so we need to create our variable for curpause here. So int curpause will start off at 0. And then we're going to need an array that can hold all of our values. Right. So if this is our example of our current section of our array, we don't know necessarily which buckets these were, but let's just assume for the sake of argument here. So let's just say this is 5, 6, 7, 8, and 9. Whatever. So in this case, begin 1 would have been 5. Begin 2 would be 8. We can see that I need 5 total buckets. So the question is how did I get to the number of buckets that I need here? It is end 2. Well, actually, you can just say end since those are the 2 things coming in. End minus begin. 9 minus 5 is 4 plus 1. Get you to the number of elements that are going to be in your temporary array. This guy. This is bucket 0, bucket 1, bucket 2, bucket 3, bucket 4. All right. And curpause is going to keep track of which one of those guys we're currently trying to fill. So now we need to go ahead and create this array for us. So I'm going to say I need an int array. We'll call this guy temp, and it's going to be a new int array of size end minus begin plus 1. Which is end minus begin plus 1, which will give us the size of that list. If instead we were dealing with the first part of this list, 0, 1, 2, 3, 4, 4 minus 0 plus 1, 5 buckets. So the math works no matter which section of our array we're looking at. What we're doing right here is actually probably the most difficult part of merge sort. After you get past the intimidation factor of the recursion, it's just keeping track of where you start and where you end and make sure you either don't leave out somebody or don't sort the same part more than once. Okay, so it's really just keeping track of the beginning and ends of the left half and the right half. And out of curiosity, as you were going through this, how many of you went down the path where you the left half of your list was working out okay, but the right half was wonky? Guessing several of you based on probably this one line right here. Okay, if you use different math for that one line right there, it would have seemingly worked for a while until it stopped working. And then you stared at it for 11 hours until you either gave up or, or whatever, but that's a normal process for merge sort. So the funny thing is the difficult part is just simple arithmetic for merge sort, mixed in with a couple of bullies with the 2 recursive calls, and we're cowering in the corner. All right, so this is our temporary array that we intend to fill up. Now we know that we are going to put this many elements into this array. Okay, so and that's temp.length number of elements. So if you want to think about this like a competition, we're going to say I'm comparing whatever's at start 1 to whatever's at start 2 and saying who is smaller, because that's the guy who's going to go at bucket 0 of temp. Then we're going to move on and have our next competition. Start 1 will move here. Who's smaller, 3 or 2? 2 is. So we'll place 2 right there. So on and so forth. We know we're going to do this 5 times. So we're going to go ahead and write a loop that goes through temp.length number of times. All right, so standard for loop, going to go through in our little example here 5 times, right? Temp.length will be 5. All right, now each time through, we want to compare the elements that we're currently considering. That is, we want to look at start 1, the value that lives at that, and start 2, the value that lives there. But we only want to compare those if both of those guys are still on their respective lists. For example, if we've already won 3 times from list 1, this guy's now pointing off the end of list 1. That is, start 1 is greater than end 1. So when start 1 is greater than end 1, we no longer have legal combatants in the start 1. So we'll just start picking our winner from start 2 from that side. So let's ask the question, if they're both legal, then we're going to do the comparison. That is, if start 1 is less than or equal to end 1, and start 2 is less than or equal to end 2, that means they're both at least pointing to real places. If start 1 is less than or equal to end 1, and start 2 is less than or equal to end 2, if both of those are true, a little comment before this guy, are both positions legal? If they're both legal, then we need to ask the follow-up question. Okay, well, is the element at start 1 less than the element at start 2? If this dot, what did I name my array? The array. This dot, the array at start 1 is less than this dot, the array at start 2. If this number is smaller than this number, then our winner is start 1, the element at start 1. So we're going to say temp at bucket curpos, which the first time through this will be 0, gets the value of this dot, the array at start 1. That was our winner in this particular fight. Start 1 plus plus. We just picked the winner. So if we use this example here, we say, which value is smaller, a 1 or a 2? 1 is the smaller value. So we will put 1 right here. And then what we're going to do is we're going to increment start 1. We also need to increment curpos, but we're going to do that regardless. Now, if the element at start 1 was not smaller than the element at start 2, that must mean that start 2 was the smaller element, or at least equal to it. and we're just deciding that the one that was the second one that was equal is the one we're going to pick. So then we'll say temp at cur pos is equal to this dot the array at bucket start 2. Start 2 plus plus. Now, regardless of which of those guys was the smaller value, we've just placed somebody at bucket temp pos and temp. Now we need to increment temp pos. Okay. Is that what I called it? Cur pos? Thank you. Cur pos, cur pos. Okay. At least I used it right in the other places. Cur pos. All right. So what did that just do? That just did that. Moved cur pos down the line because the next thing we're going to place is right here. Okay. Now, all that logic we just put in there only happens if both start 1 and start 2 are pointing to legal places on their respective arrays. Else if they're not both legal, that means at least one of them, well, that means in this case, since we know exactly how many times we're going to go through, that means one of them is currently illegal. Okay, so if we didn't get into this if statement where both of them are legal, one of them is illegal. So we'll go ahead and ask if start 1 is greater than end 1. That's asking the question, did start 1 walk off the end of its list? So if start 1 is now bigger than end 1, start 1 is past the end of his part of the list. If that's true, then by default, start 2 is the winner. So if start 1's illegal, we'll go ahead and say cur pos is equal to start 2, and then increment start 2. I'm going to be moving this cur pos here, by the way, in a minute, but we'll leave it there for now. Else, if they weren't both legal and start 1 was not the illegal one, it must have been start 2 that was the illegal one. Therefore, we'll just hand the victory to start 1. All right. Now, no matter what we just did there, we placed some value into temp. So we always want cur pos to increment by 1 each time through our loop. Now, we could have used I as our counter as we went through here. All right. I chose to use a completely separate variable to keep track of where we were in there. We're going to reuse that variable here in a second. All right. So again, if they're both legal, decide which is the smaller value and put the right guy there and increment the guy who won. If only start 2 was legal, grab the next value from start 2, increment start 2. If only start 1 was legal, grab the next value from start 1, increment start 1. Regardless of which of these conditionals we entered, we just placed some value in our temp list, so we're going to increment cur pos. All right. So when this for loop is done, temp holds our values sorted for this portion of the list. So now we have to copy them back over. That is to say, we need to take bucket 0. So if I just keep going through the paces here, so 2 would have been the next winner. 3 versus 7. 3 is the next winner. 5 versus 7. 5 is the next winner. Illegal position compared to 7. 7 is our winner. Our for loop just died a natural death because we knew exactly how many things we were going to be placing. So we never have to ask that question. Well, are they both illegal now? Although you could have written a while loop that just kept going until they were both illegal. You would have gone through the same number of times. All right, but right now, this is temp right here. So temp currently looks like this. The portion of our real array currently looks like that. We need to overwrite this portion with the contents of temp. All right. So what we're going to do here is we're going to say cur pause is equal to begin, which is the first part of that actual part of our array that we're working with. We know temp is going to be a bucket 0. Now we'll write a stock for loop for int I is equal to 0. I is less than temp.length. I plus plus. So we're going to go through every element of temp, bucket 0, bucket 1, bucket 2, and we're going to overwrite our array at bucket cur pause, increment cur pause, at cur pause. So we'll overwrite bucket 5, then 6, then 7, whatever it is. So we'll say this dot the array at bucket cur pause is equal to temp at bucket I cur pause plus plus. And at this point, our merge step is done. We've played the little game between the left half and the right half, figuring out who our winners are. We filled up temp with the winners, then we wrote the original array with our correctly ordered values in that portion of the array. So this guy now is done. That's our merge step. We do the merge step after both calls to merge sort have returned. Now what I'm going to do here is I'm just going to comment out our little display things so we don't get 4,000 things displayed along the way. All right, good, because we're on the last minute. And there's our sorted array. Go ahead.
I guess it's less of an interruption to what we put in. We have a couple GPS flow events coming up. Tonight we have our typical 4:30 to 6 o'clock study session. So if you need help with homework, you can come there, or if you just want to hang out with us upper class. And then Wednesday, we're resting. We have a GitHub seminar. So we're going to teach you how to use GitHub. It's a very important tool for the industry, but for this program especially. So it's going to be something you're going to use. So I highly recommend you come to that.
Remember when you wrote merge sort?
Vaguely.
If you block that out now?
Oh yeah.
Yeah, that
it was with Blade. It wasn't with you. So I'm kidding.
No, you would have done merge sort in my class. You had Blade for 300.
We did do merge sort.
You coward. You've blocked it out. All right. So questions about the CS Club stuff, good opportunity to ask questions. This would have been a good thing to, if you were struggling with this assignment, to go and ask them questions. So do take advantage of that. I'll post this code up. So you see we do now have our sorted array. As you saw, very easy, trivial code. This is complex code, obviously. So I'll share it. It'll get on Slack, walk through it, make sure you understand what's happening. Each individual step was not very difficult, but putting them all together in the right order, all hard problems are made up of a bunch of easy parts. All right, no homework for Wednesday. I'll see everybody then.